All right, we are going to hop into chapter 4 where we talk about hypothesis testing for the first time. So, hypothesis testing is what we are going to focus on for the rest of the course. And when we talk about hypothesis testing, we're talking about 5 steps that we're going to use for every time we do a hypothesis testing situation. So, we will get used to those. Page 110 in the newest edition of the book, the 6th edition, starts talking about the core logic of hypothesis testing with the 5 steps. So the idea of chapter 4 is to determine if a score on any kind of variable that we're measuring is significantly different than what we would expect to see. Now that's a very vague statement, but that's how we start. When we talk about these ideas, we need to start with just the ideas, and then we're going to start to apply them to an example. And this example is going to be a pretty straightforward demonstration of some kind of principle that is related to developmental issues in children. So let's go ahead and hop into the first slide where we're going to talk about some symbols. Now, we're familiar with the idea of sample statistics, that is the mean, standard deviation, and variance. Those are the 3 big ones that we focused on in terms of inferential statistics. Now, we have talked about measures of central tendency like mean, median, and mode, but we're going to be working with scale level variables, so we're going to be using the mean for those. One of the ideas that we have to really distinguish here is a sample and a population. A population is a collection of individuals or scores that make up everything that we're interested in. For example, if we're talking about a classroom of students, the entire classroom of students is our population. If I'm only concerned about that one classroom, that's my entire population. We don't need to have everybody in the world to be in a population. If you're interested in looking at the number of people who have committed some kind of crime, then all of those people who have committed that crime in that county, for example, would be your population. A sample is a small subset of a population. So if I were looking in a classroom and I wanted to sample the population of students in that classroom, I might pick the front row and that would be my sample. Now, when we talk about a sample and a population, we're talking about 2 different sets of symbols that mean the same thing, but we have to keep them separate because we can calculate the mean of a sample and the mean of a population. For example, go away. For example, we can have the mean of a sample, and that is a capital M, and the mean of the population is a capital mu. That's mu, is a Greek letter. The sample symbol for standard deviation is SD. The population symbol for standard deviation is sigma. It's a lowercase sigma. For variance, it's SD squared, and for population, or excuse me, for the sample, the variance is SD squared. For the population, it is sigma squared. So these are symbols. They don't do any real math and they don't mean anything except for to symbolize the difference between the sample mean and the population mean. Some important terms that we need to be familiar with in this chapter are hypothesis, theory, null hypothesis, alternate or research hypothesis, comparison distribution, and cutoff score. I'm just going to briefly go over these so that we are familiar with them. If you need to go back and brush up on them, you sure can. But these are in the book, and you can find out what they mean from there. I'm going to try to use some consistent language that I'll be using the rest of the course to talk about these. That way, when you hear me talking about them, you understand what they go with. So a hypothesis is kind of an educated guess. That tends to be what most people think of when they think of a hypothesis. Really what we mean by a hypothesis is, what do we expect to happen if there is some kind of difference or significant change happening? So I might hypothesize that if it's cloudy tomorrow, I'm not going to get a suntan. Now, that'd probably be wrong because we know that we can get sunburnt through clouds, but generally I'm not going to go outside if it's cloudy and I'm not going to get a suntan. But that's kind of the hypothesis. Okay. The theory is what drives the hypothesis. We're not going to delve into theory too much, but we do need to understand that The way that we think about the world will determine our hypothesis, what we think is going to happen. Now, specifically in terms of what we think is going to happen, we have a null hypothesis and an alternate or research hypothesis. I probably use research hypothesis more than I use alternate hypothesis when I describe it, but just know that if I say alternate or research, I'm talking about the same thing. Let me start with the alternate or the research hypothesis. The research hypothesis is what we think will happen if there is an effect. Okay? So if I think that most people will stay inside when it's cloudy, then I am saying that that's what's going to happen if there is an effect. If cloudiness has an impact on people going outside, then I will see fewer people outside. The null hypothesis is what happens if the research hypothesis is not true. For example, if I think that people will not go outside because it's cloudy, and they actually do go outside, and that there's no difference between how many people go outside when it's cloudy and how many people go outside when it's sunny, then the null hypothesis is true. We're going to spend a lot of time focusing on the null hypothesis. That is there no difference? If the weather outside does not make a difference, then I am supporting the null hypothesis. The comparison distribution is the distribution of scores that I am comparing my sample to. If I want to see if 3 people in a classroom have higher scores because they attended a study session, then I'm going to compare my sample of 3 students to the rest of the students in the class. The rest of the students in my class become a comparison distribution, and I'm going to determine if my sample behaves differently than the comparison distribution. My cutoff score, and we'll talk a lot about these when we talk about how to calculate z-scores in terms of hypothesis testing. But my cutoff score is the score at which I will reject or fail to reject the null hypothesis. If I use the example that I talked about with the comparison distribution of the sample of 3 students compared to the population of students in the classroom, then I'm talking about a null hypothesis situation to where the 3 students who attended the study session will have the same scores as the students who did not go to the study sessions. That might mean that the study session did not make a difference. That would support the null hypothesis, which is what occurs when there is no difference. The cutoff score would be the score that I would say would be a significant change if my sample obtained it. For example, if I had a sample of students that got an 80% on an exam because they went to a study session, and the rest of my students only got a 60%, I would probably think that that is significant. But I have to select a point at which I think it's significant. So let's say that I thought that if my students who studied get a 75% or better meant that a study session was helpful, then I would look at my sample score and see if it's higher than that 75%. So if the scores are significantly above 75, then we would consider that to be significant. Because our cutoff score was 75%, we would think that the people who went to the study session somehow were impacted by it more than those who weren't. If the scores that the students who attended the study session obtained were 75 or less, then we would probably not consider that to be significant, and they would score at the same level as our comparison distribution. And again, that cutoff score, I'm just kind of using an arbitrary cutoff score for this demonstration, but the cutoff score will be very specific, and it will equate to a certain percentage of scores that you would expect to see. So let's take a look at an example that we're going to set up for the rest of this chapter in order to determine what kind of hypothesis testing procedure that we can use depending on a situation based on developmental psychology. So let's take a look at this example and just the brief demonstration of the normal curve with our population, standard deviation, and mean. So here's our example. Let's say that we have a bunch of babies that are given a vitamin. One group of babies is given a vitamin that does nothing, so the vitamin's a placebo. Of all of those babies, and it doesn't matter how many babies there are just a lot of them. One baby is given an enriched vitamin to see if the vitamin has an impact on walking ages. So we're going to give one single baby an enriched vitamin to see if its walking age is impacted by it. And we're going to compare that baby's walking ages to the distribution of babies that were given the placebo, the one that did nothing. All right, so now we're starting to think about these terms again. We have a comparison distribution. We're going to compare our sample, a sample of one baby in this case, to a distribution of babies that were given a regular vitamin. So we're going to compare our single baby to a distribution of babies that were given a regular vitamin. And we're going to see if our baby has a different walking age because of the vitamin. Below is a curve that determines the distribution of babies who took the placebo. More specifically, this is a distribution that talks about the breakdown of standard deviations and the percentages. Notice that we're using population symbols, the mu and the sigmas, to determine the standard deviations for this distribution because we are using a comparison distribution of babies' walking ages who took the regular vitamin. That is, this is our population parameter. So we have the mean and the standard deviation that's 1 above the mean, standard deviation that's 2 above the mean, standard deviation that's 1 below the mean, standard deviation that's 2 below the mean. So let's put some numbers to this with our example. In our example, the average walking age of the babies who took the placebo, who took the regular vitamin, had a walking age of 14 months, a standard deviation of 3 months, meaning that if you go 1 standard deviation above the mean, you walk at 17 months because that's 14 plus 3. The second standard deviation above the mean is at 20 months because that's 17 plus 20. Going below the mean, if a baby walks 3 months earlier, then they walk at 11 months. That's 1 standard deviation below the mean. And then if a baby who took a regular vitamin walks at 8 months, that is 2 standard deviations below the mean, or 8 months. That is reiterated here, where we just summarize our descriptive statistics that the mean of the population that we're comparing our sample to is 14 months with a standard deviation of 3. So maybe I'll just make a quick note that this is our comparison distribution. I'm going to abbreviate distribution with dist. I think we can handle that. So here are a few questions about this distribution just to kind of prime the idea of hypothesis testing. So just generally, based on our distribution of babies that took a regular vitamin, at what age would you expect babies to walk? Generally, you can say that 96% of the babies would walk between 8 and 20 months because we know that 96% of the scores fall between 2 standard deviations, plus or minus. Some people might say, yeah, but we know that 68% of the babies, so even more than half, will still walk between 11 and 17 months. So we expect babies to walk at a certain age based on our comparison distribution. What would we think about a baby that walked at 6 months? So if a baby walks at 6 months, so way down here, what would we think about that? We might think, oh wow, that baby walked at 6 months, which is probably close to less than 1% of all the babies in this comparison distribution. Okay. So we would think that that is early. But what if the reason that the baby walked at 6 months was because they took the enriched vitamin? Now all of a sudden we're thinking to ourselves, well, wait a second. This baby didn't take the regular vitamin. It took an enriched vitamin and walked really early compared to the rest of these babies. You might start to think that, oh, maybe this enriched vitamin has an effect on walking ages because it does not walk at the same ages as the babies that took the regular vitamin. The key to null hypothesis testing is to determine if our sample behaves differently than a situation where there is no effect happening. So in this comparison distribution, this is the distribution of babies that took the regular vitamin. There is no effect occurring. We are not suspecting that there is an impact caused by an enriched vitamin because none of these babies took the enriched vitamin. If an enriched vitamin baby walked at 6 months, we would say, okay, this baby is different than the situation where the babies were not taking that vitamin. That is the key to null hypothesis testing. Let's break this down a little bit easier. Hypothesis testing is about determining whether our results, that's an our, not an out, our results are expected based on the comparison distribution. That is, are the results we saw different from what we would expect if there were no difference? I know that sounds like an inside-out sentence, but I promise it's right. It just is inside out. So another way of saying is, if some effect is present, we will know because our results are unlike the distribution that has no treatment effect. So with the baby vitamin example, if some effect is present, so if a baby walks really early, we will know it's because our results are unlike the distribution that has no treatment effect. So we know that the baby that walks really early is walking early because it's not like the rest of the babies who took the regular vitamin. An even simpler way is to say that an alternative hypothesis is that this egg is different than an egg that has not been dyed. Oh look, it's a blue Easter egg. This egg is different than an egg that has not been dyed. Okay? The null hypothesis is that this egg is not different than an egg that has not been dyed. Again, it sounds inside out, but it's correct way to say it. The null hypothesis is that the results that we found are not different than the results if there is no effect. So if an egg has not been dyed, then it will look like other eggs that have not been dyed. If an egg has been dyed, it will look different than the egg that has not been dyed. This is the key to null hypothesis testing. Let's take a look at how we might situate some language around the idea of null hypothesis testing. So we're back to our enriched baby example. We're going to throw in a couple symbols as well. The symbol for alternative or the research hypothesis is H sub 1. That is not HI, it's not H, the big number 1, it is H subscript 1. And the alternative hypothesis is that babies with the enriched vitamin will walk sooner than those with the regular vitamin. Okay, so that's another way of saying that is that if the enriched vitamin makes it different, that the babies will walk sooner. Another way of saying this with some symbols is the alternative or the research hypothesis is that babies with the enriched vitamin will be less than babies with the regular vitamin. And remember, we're measuring this in terms of months. So babies with the enriched vitamin will walk earlier or have a lower score or walk at fewer months than babies with the regular vitamin. The null hypothesis is that babies with the enriched vitamin will walk at the same age, or at least not significantly different, than those with the regular vitamin. Okay, so babies with the enriched vitamin will walk at the same age as those with the regular vitamin. Another way of saying that with statistical symbols is H sub 0, or the null hypothesis is that babies with the enriched vitamin will have a walking age in months that is greater than or equal to babies with the regular vitamin. Remember, the null hypothesis is what we would expect if there were no difference between the test group, or our sample in this case, and the comparison distribution, also known as the control. In order to test our hypothesis, more specifically the null hypothesis, we're going to step through 5 steps to test. We have the summary of the 5 steps. I use the language pretty consistently, but I might not use it verbatim. So here's what we do. We restate the question as an alternate hypothesis and a null hypothesis, and we identify the populations, which is known as the sample and comparison groups. So every alternative and null hypothesis has a research question. So we're going to restate the research question, and then we're going to create a null and alternative hypothesis. We're going to determine the characteristics of the comparison distribution. So we need to find out what the distribution of scores looks like where there is no treatment effect. That way we can compare our sample to it. We need to find out what the cutoff score is on the comparison distribution that we will use to reject or fail to reject the null hypothesis. We then need to determine our sample score on the comparison distribution, and then step 5 is to decide whether to reject the null hypothesis. Let's take a look at step 1 with our example. So in step 1, we restate the question as an alternate hypothesis and a null hypothesis and identify the populations. Now, one of the things that I really don't like about the book is that it says identify the populations. Well, that's kind of misleading because we have a sample and a population. So really what we want to do is identify the groups that we are comparing. And that's our sample and our comparison groups. So if we identify the populations, we do that by saying that population 1 is the enriched vitamin group and population 2 is the regular vitamin group. So the alternate hypothesis is that babies with the enriched vitamin will walk sooner than babies with the regular vitamin. Another way of saying that is that population 1 will have a lower score than population 2. The null hypothesis, which is the hypothesis that states that there is no difference between the groups, is that babies with the enriched vitamin will walk at the same age or later than babies with the enriched vitamin. Another way of saying that is that population 1 will be greater than or equal to population 2. Now, once we identify the hypotheses and the populations, we can go forward and find out what we're going to compare our sample to in order to determine if we have a significant difference. So in step 2, we determine the characteristics of the comparison distribution. We've already kind of looked at this, but we'll restate it. The comparison distribution is based on a bunch of babies that have taken a regular vitamin. And we're going to compare the walking age of our baby that took the enriched vitamin to these scores. So we have a mean of 14 months and a standard deviation of 3 months. This is what our comparison distribution looks like. If our baby walks significantly earlier than this distribution, then the score of those individual baby that took the enriched vitamin will be somewhere in this area. Okay, we're going to take a look and see where that specifically is in the next step. So this is our comparison distribution. We are going to calculate some kind of spot on this curve that determines where our null hypothesis will be rejected. Let's take a look at step 3. In step 3, we are going to determine the cutoff score where we will reject the null hypothesis. Now, this is a consideration that we have to make that this book uses in order to teach the principle. We are going to use an unconventional cutoff score for this example. That means that this is not a cutoff score that is widely agreed on. It is a cutoff score that is easy for learning. Okay? So when we talk about this rejection zone or this cutoff score, just know that it's not conventional and that we're going to use other cutoff scores going forward, but for the sake of learning, we're just using a round number. So in the example, we are told that we are going to use a cutoff score of -2 or a z-score equal to -2. What that means is that we are going to reject the null hypothesis if the z-score for our example, for our sample, is less than -2. That'll make a little bit more sense in the next step. But let's take a look at what we mean by rejecting the null hypothesis. First step, we recognized that the babies that walk with that have the enriched vitamin will walk at the same age or later than the babies with the regular vitamin if the null hypothesis is true. By the way, I recognize I made an error earlier. I think that this said enriched. It should say regular, and I've made that change. So the null hypothesis is that babies with the enriched vitamin will walk at the same age or later than babies with the regular vitamin. What that means is that if the null hypothesis is true, then that means that a baby will walk at the same age or later than the babies in the comparison distribution. And when we say that, we don't really mean that they will walk later than every other baby. What we mean is that they will walk at the same age or later than some arbitrary cutoff score. In this case, later is going to be a very planned cutoff score. But what that means is that if a baby walks at 8 months or later, then that is the null hypothesis, that there is no difference. Then our baby would walk later than what we would expect if the enriched vitamin made a difference. If the baby walks sooner than 8 months, what that means is that we reject the idea that the baby that takes the enriched vitamin walks later than the babies that took the regular vitamin. So if our z-score, if our sample score is somewhere in this area, so if it's in this triangle here, then what that means is that we have a significant finding and that we can reject the null hypothesis that there is no difference between the baby that took the enriched vitamin and the babies that took the regular vitamin. Now, I told you earlier that we are going to use a cutoff z-score So what that means for the null hypothesis is that if our sample's z-score, that is, if the z-score of our baby that walked at a particular age is less than -2, then we will reject the idea that there is no difference or that babies walk later or at the same age who took the regular vitamin. So if this enriched vitamin baby walks at an age that is at 8 months or greater, then we fail to reject the null hypothesis. What that means is that the baby walks in about the same area as babies that take the regular vitamin. We want our baby to walk earlier, and if the baby walks earlier than most of the other babies, then we will consider that to be a significant finding. In this particular case, we recognize that if a baby has a walking age of 8 months or less, then that means that this baby is walking earlier than 98% of the other babies based on the breakdown of percentages at each standard deviation. So remember that in the tail we have 2%, and then we have 14% and 34 and 34 and 14 and 2. So if a baby walks significantly earlier than 8 months, then that means that they're walking earlier than 98% of the other babies, and that's a significant finding. So let's calculate our sample's walking age and compare it to the z-scores of the other babies. In step 4, we're going to determine the sample's score on the comparison distribution. That means we need to compare our sample score from the example in the book to the comparison distribution that we identified earlier. Let me get my pen out, and we're going to do green. So, our baby's walking age is 6 months. That is the number of months that the baby walked at when he took the enriched vitamin. The average walking age of the other babies was 14, with a standard deviation of 3 months. We are going to use a version of the z-score formula in order to find out what the z-score is for our baby that walked at 6 months compared to our comparison distribution. So our comparison distribution has walking age in months, 8, 11, 14, 17, and 20, and also the z-scores for each of those walking ages. Remember, the z-score of 0 is equal to the mean. A z-score of 1 is 1 standard deviation above the mean. -1, 1 standard deviation below the mean, and so on. We're going to use this formula, which is the z-score for our sample is equal to the score that our baby walked at minus the mean of the scores of the babies who took the regular vitamin divided by the standard deviation of the scores that the babies who took the regular vitamin walked at. And so I'm going to use that formula, and I'm going to just plug in some numbers here. So z is equal to, x in this case is our raw score, which is 6, minus the mean, which is 14. Remember, that's population mean of the population, divided by the population standard deviation, which was 3. That is equal to -8 divided by 3, which is equal to -2.67. What that means is that our baby that took the enriched vitamin and walked at 6 months walked at 2.67 standard deviations below the mean. So that's about 2 1/3 standard deviations below the mean. Remember, our cutoff score was at 2 standard deviations or a z-score equal to 2. And we declared that if our sample score is below this line, then it would be a reject null situation. Now we're getting a little bit ahead of ourselves because we're going to need to do this in step 5. All we needed to do in this step was to find this number, negative 2.67. So we've done that. So our baby's walking age is 2.6 standard deviations below the mean. Negative 2.67, and this is our sample. In step 5, we are going to decide whether or not to reject the null hypothesis. In step 5, we kind of already did this in step 4, but we're going to bring forward some information. Our sample's z-score was negative 2.67. What that means is our sample z-score is somewhere in this area, negative 2.67. What that means is that we reject the null hypothesis. Remember, the null hypothesis is that the babies who took the enriched vitamin will walk at the same age or later than the babies that took the regular vitamin. We reject that idea. We reject it because our sample z-score falls in this rejection zone visually, and also because there is a difference in our sample z-score compared to our cutoff z-score. So let's plug in some information. So our sample z-score is negative 2.67. Our cutoff z-score, was 2 standard deviations below the mean. So our cutoff was negative 2. Now, way back in step number 1, we calculated, or we discovered what our null hypothesis was going to be. Our null hypothesis was that population 1, which is what our sample is, will be greater than or equal to population 2. What we do here is we take this statement, population 1 will be greater than or equal to population 2. That's our null hypothesis. We're going to bring that statement forward, and we're going to take the symbol that we use, greater than or equal to, and we're going to test this. So our null hypothesis was that our sample z-score, which is population 1, will be greater than or equal to population 2, which is our cutoff or our comparison distribution. We have a null hypothesis that says that population 1 will be greater than or equal to population 2. If I bring down my statistic that we found, I can use this formula to make a decision. This is a very straightforward thing. Is negative 2.67 greater than or equal to negative 2? The answer to that is no. Okay, so if we say no to this, what we are rejecting is our null hypothesis. Negative 2.67 is not greater than or equal to negative 2. Okay, negative 2.67 is less than negative 2, which is what we found graphically here. So this means that we reject the null hypothesis. We reject the idea that our sample is greater than or equal to our population. What we have found is a significant finding. What you can say is this. With respect to our research question, does the enriched vitamin decrease walking ages? So do babies walk earlier who take the enriched vitamin? We have a result. We tested the null hypothesis that the babies who take the enriched vitamin will walk later than or at the same age as children or babies who take regular vitamins. We tested that null hypothesis. We found that babies that take the enriched vitamin walk sooner than babies that take the regular vitamin. Therefore, we reject the null hypothesis, which states that babies who take the enriched vitamin walk later or at the same age as those who take the regular vitamin. We reject the null hypothesis, and we have a significant finding that states that babies the enriched vitamin will walk significantly earlier than babies who take the regular vitamin. In this particular case, you'll notice one thing. We had a hypothesis that suggested that there is a change in one direction, that we were expecting babies to walk sooner. It could have been that we expected babies to walk later who took an enriched vitamin. Although it's not theoretically sound that we give a baby a vitamin and they walk later, we could have still had the hypothesis. There is also a situation where we don't know what kind of effect something might have, so we say that we're going to say that a significant result is either if a baby walks really early or really late, and we'll accept either, but we're not sure which way it's going to go. In those cases, we are talking about the difference between a one-tailed hypothesis and a two-tailed hypothesis. So let's go ahead and get into that, and then we're going to run this same example, but we're going to use a different kind of hypothesis. Here you can plainly see why they call it a one-tailed versus two-tailed test. So with a one-tailed test, let me start with the example that we just did. With the baby walking example, we used a one-tailed test, meaning that we were considering a change in a negative direction to determine significance. So we knew that if our result fell in this particular cutoff zone, then we would have a significant result. Or, this is the big or we could have looked at the positive direction to determine if there was going to be a significant positive change. So that meant that the baby would walk significantly later. If that were the case, then we would be considering significant changes in a positive direction. So, in the case of a two-tailed test, we are trying to determine if there is significant in both directions. That doesn't mean that you get one test that has significant changes in both directions at the same time. What we're saying is that we will consider a significant change in a negative direction and a positive direction. So what that effectively does is it says that there's a possibility of finding significant positive changes and significant negative changes. In the case of a one-tailed test, if we had a baby that walked at 6 months, we found that it was a significant change. If we were still looking at a one-tailed test from last time, from that example, and a baby walked at 30 months for the first time, that would be way out here. But that would not have been a significant change because we were only looking at a negative change in one direction. We would not have been considering the top because we're only looking at one or the other. So we would have looked for a negative change. The baby would have walked at 30 months, which is really, really late, but it would not have been significant because the way that we set up our hypothesis. Say that we set up a hypothesis that says that an enriched vitamin will have an effect on baby walking ages, but we don't suspect a change in either direction. We just think that it'll make a change, but we don't know if it's positive or negative. If we use this two-tailed test, we would find a significant result if a baby walked really early or if a baby walked really, really late. So we would be considering a change in two directions at the same time. Now, when we do that, we also have to consider the fact that our significance changes. When we consider the number of tails, we have to also consider the likelihood that our result is to happen. And we talk about likelihoods in statistics in terms of probabilities. So the probability of obtaining a significant result, we like it to be less than 5%. Now, here it's expressed as p is less than 0.05 or 0.05. 0.05 is okay too. That means that the probability of finding a significant result is less than 0.5%, meaning that if a result does occur less than 5% of the time on our distribution, then we consider it to be significant. So what we do is we assess that there is some kind of area, and again, this is just a graphical representation, it's not perfect. So with a one-tailed test, we are considering a zone or a cutoff area that accounts for 5% of the curve. And again, this is just a rough drawing of it. So inside of this zone lies 5% of the scores. If our sample falls in there, then it occurs less than 5% of the time, and that is a significant result. By the way, this could also be expressed positively, but for the sake of this drawing, I've only expressed it negatively. As you'll notice that when you have a one-tailed test, you have a larger rejection zone. It looks larger, but it's the same probability. In a two-tailed test, all we do is split the significance. What that means is that inside of this zone is 2.5%. Inside of this zone is 2.5%. And what that means is that we're still looking at a 5% probability of finding our result. The difference is that we split it between the positive and negative sides of our curve. There is a chance that you might run into a hypothesis testing procedure that uses a cutoff of 1% or 0.01. We don't use those in this class because it's not a conventional level of significance for statistical work in the social sciences. But just to show you what happens is that this rejection zone for 1% is even smaller than the rejection zone for 5%. And for a two-tailed test, it's even smaller. Again, this is a graphical representation as a drawing, so it's not to scale, but what we're demonstrating here is that these cutoff regions become very small. So this is actually a 0.005% zone in this side and 0.005% in the other side, and what that equates to is 0.01 or 1%. Just keep in mind that for a one-tailed test, we can use either negative side or the positive side. For a two-tailed test, we must use both sides. When we talk about one-tailed versus two-tailed, that is synonymous with directional versus non-directional test. When you think one-tailed, think directional. When you think two-tailed, think non-directional. When we're concerned with significant differences in one direction, like in the baby vitamin example from above or before, we use a directional hypothesis, which means that we are looking for a population 1 change that is either less than or greater than, if we're looking at the alternate hypothesis. For the null hypothesis, we are determining if our result is like the population that we are comparing it to, and that it is greater than or equal to or less than or equal to, depending on which side of the curve you're looking at. All right. When we are concerned with significant differences in either direction, so a non-directional test, also known as a two-tailed test, we use a non-directional hypothesis. So the alternative hypothesis is that the populations are not the same. That means that they are either less than or greater than, but whatever they are, they're not the same. And the null hypothesis is that they are the same. Here is a cheat sheet that you can use to help you keep your symbols straight. So for the null hypothesis, for one-tailed is either less than or equal to or greater than or equal to. And for a null hypothesis with two tails, the symbol is equal to. For an alternative hypothesis, the symbol is either less than or greater than, or for a two-tailed alternative hypothesis, the symbol is not equal to. The cutoffs that we use for directional hypotheses are similar to what we use for a non-directional hypothesis. The difference is that we are considering a change in either direction and splitting the significance. So for a directional hypothesis, we generally want to know when our result occurs 5% or less of the time. That means that if our result falls into this region, that means that it occurs less than 5% on the comparison distribution. By the way, this could also be expressed positively, but not both at the same time for a directional hypothesis. For a non-directional hypothesis, we are concerned with how likely is our result to occur, and if it is less than 5% of the time, then we consider it to be significant. But what we do is we split this 5% significance and we consider 2.5% positively and 2.5% negatively at the same time. Now, you might be thinking to yourself, oh crap, how do I know when my result occurs 5% of the time? Well, I'll save you some work. And really, we're only going to be using this top row, but I'm just recreating the grid from the books to include 1%. So for a probability of less than 5% or p less than 5 or 0.05, the one-tailed z-score cutoff is negative 1.64 or positive 1.64. That's a big or. Remember, with a one-tailed test, we're only looking at a change negatively or positively. For a two-tailed test, we're looking at negative 1.96 and positive 1.96. What that means is that for a two-tailed test, we are looking at a z-score that is positive 1.96 and negative 1.96. And if our result falls in either one of these two rejection areas, then we have a significant result. If our sample z-score falls in an area that is not in the rejection zone, then that means we have a non-significant result and we cannot reject the null hypothesis. All right, that was a lot of mumbo jumbo. Let's jump into an example and walk through it. That way we can put a little bit of practice to it. We're going to use the same baby walking scenario from last class. This is designed for a two-part class, but for online, it's the same lecture. So here's the research question. Will an enriched vitamin affect the walking age of a child? So what we're saying here is, if I give a child an enriched vitamin, will it affect the walking age? Now listen to the language. Will it affect the walking age? I'm not saying, will it increase the walking age? I'm not saying, will it decrease the walking age? I just want to know if it changes the walking age at all. When you hear that language, you're talking about a non-directional or two-tailed test, meaning I don't know what it's going to do, but I'm looking for a significant result in either direction. So here's some information. We noticed that a baby that took the enriched vitamin walked at an age of 19 months. We're going to use a cutoff probability of 5% of 0.05, and we want to know, is the sample score significant? What this means is, does our sample score, so does 19 months occur less than 5% on the comparison distribution? We're going to walk through these 5 steps to come up with the decision. Step number 1 is to restate the research question as a null and alternative hypothesis and identify the populations. Now, because we've already done an example, we're going to kind of go through this a little bit quicker for the sake of time. So the research question was, will a baby walk at a different age because they've taken the enriched vitamin? So we're going to have two populations. So population 1 is the enriched vitamin. Okay. And population 2 is the regular vitamin. So I'm going to abbreviate some things for the sake of time. The alternative hypothesis is that babies with the enriched vitamin will walk at an age that's different than babies that took the regular vitamin. So I'm going to say that population 1, the enriched vitamin baby, will not walk at the same age as the babies that take the regular vitamin. So population 1 will not be the same as population 2. The null hypothesis, again, you can refer to that that grid that tells you how to use your symbols, is that population 1 will be the same as population 2. Okay, so just kind of maybe briefly to graphically represent what this might look like, is that on this curve, population 1 will not be like population 2, meaning that population 1 will have some kind of score that's either positive or some kind of score that's negative, one or the other, because this is a two-tailed test. For the null hypothesis, what we're really saying is that, oh, it's a bad curve, is that population 1 will behave like population 2, so they will be the same. Okay. So that means the enriched vitamin baby in the alternative hypothesis will somehow be in one of these rejection zones. And in the null hypothesis, if the null hypothesis is true, then the baby will behave like the rest of the population. We're trying to reject this hypothesis. This is what we're trying to address. We want to reject this idea, which starts to support the alternative hypothesis, but all we say is that we reject the null hypothesis. Step 2 is to determine the characteristics of the comparison distribution. Now remember, the comparison distribution is the babies that took the regular vitamin. And that's not going to change for this example, it's the same. And as you recall, the mean walking age for babies that took the regular vitamin is 14, with their standard deviation equal to 3. So that means we have a mean of 14 and a standard deviation of 3 that looks like this. And then we have the negative side. So this is in terms of months. So this is our raw score scale. Our z-scale looks like this. The mean is 0, and you got +1, +2, -1, -2. Now, we do know from the narrative of the example, the actual score of the baby that walked with the enriched vitamins was 19 months. That was from the example here. See? 19 months. So we need to find the characteristics of the comparison distribution. We've done that. The characteristics of the comparison distribution is that we are comparing our sample, our baby of one, or sample of one baby, and we're comparing that sample to a distribution of babies that took a regular vitamin that had a mean of 14, a standard deviation of 3. Step 3, we want to determine the cutoff score on the comparison distribution where we will reject the null hypothesis. Well, in the example, we are using a cutoff probability of 5%, and we know that this is a two-tailed test because of the way that the question was asked. So that means that we are using a two-tailed test, and we're using the probability of less than 0.05. By the way, if you want to sound smart, another way of saying that is that the alpha level is equal to 0.05. That's a cheap way to sound smart because those are the same thing. So the alpha level is 0.05, meaning that we will reject the null hypothesis if our results occur less than 5% of the time. So what we need to do then is to find what our cutoff zones look like here, what our cutoff scores are. Well, what we can do is we can refer to our chart that tells us what kind of z-scores we're using to cut off our significance. So what that means is that we look for the row that says probability is less than 0.05, and this is a two-tailed test. So we are looking at rejecting our null hypothesis if the sample score falls outside of -1.96 and positive 1.96 standard deviations. So I can go back to step number 3, and I can plug in our cutoff zones. So z is -1.96, which is right about there, and positive 1.96, which is right about there. So we will reject the null, which states that those scores are similar, if our result falls in one of those regions. And again, this is 14, 17, 20, 11, and 8. And a z-score of 0, +1, +2, -1, -2. So our cutoffs are positive 1.96 and -1.96. So if our result falls in either of these rejection zones, then we will have a significant result. And you can already suspect that that 19 months might be on the positive side. So we know that. So what we do next is we determine the sample score on the comparison distribution. So again, our comparison distribution looks like this. And our cutoff zones are in this area, -1.96 and positive 1.96. We need to determine the sample score on the comparison distribution. And we do that by using that same z-score formula. Z equals x minus the mean of the population divided by standard deviation of the population. The information that we had from step 2 was that the mean of the population is 14, which is also expressed here because the mean is the middle of the curve. Standard deviation is equal to 3, which is expressed by the distance between each score and standard deviations. And our sample score is 19. We plug our information into our z formula, and we get Z is equal to 19 minus 14 divided by 3, which is equal to 5 divided by 3, which is equal to positive 1.67. I rounded a little bit. So our sample's z-score of 19 months, and I'm just going to kind of maybe draw that in here, 19 months has a z-score of positive 1.67. Let me draw that in green. Positive 1.67. This is our sample z-score, which is, remember, population 1. So our population 1, or our sample z-score, is 1.67. So the baby that took the enriched vitamin walked at an age of 19 months, and that has a z-score of positive 1.67. We decided that we were going to cut off our result, or we were going to consider our result significant if it had a z-score either greater than 1.96 or less than negative 1.96. So we can kind of see already that we're going to reject, or excuse me, we're going to fail to reject the null hypothesis. We're going to kind of agree that our result is what we would expect compared to our comparison distribution. But we're still going to go through step 5 to confirm it. So in step 5, what we do is we bring forward our null hypothesis. And our null hypothesis was that population 1 will have a score that is similar to population 2. So if we plug in what our cutoff regions were, approximately negative 1.96 and positive 1.96, we can then also plug in what our score was that we found, which was positive 1.67, which is somewhere in here. So our baby score is positive 1.67. And we remember also from step number 3 that we declared that we would reject the null if our result fell in any of those 2 rejection zones. It didn't, by the way, kind of a spoiler alert. But what we do is we bring forward our symbols, and what we do is a very interesting thing with the two-tailed test. We want to know if our score falls inside of a zone that is between negative 1.96 and positive 1.96. If it does, then we can agree with the null hypothesis. So here's what we do. We plug in our rejection zone. So we have a rejection of negative 1.96, when we also have one of positive 1.96. In between that, we have our sample's z-score. And I want to know, because this is a null hypothesis, if this score of 1.67 is between negative 1.96 and positive 1.96. If this is the case, then my score will fall between negative 1.96 and positive 1.96. I can agree with this, and I can agree with the null hypothesis. So I have to do a couple of things. I have to test 2 equations. It's really easy. Is negative 1.96 less than or equal to positive 1.67? Well, the answer is yes. That checks out. Okay, negative 1.96 is less than positive 1.67. The next step is positive 1.67 less than or equal to positive 1.96? That is true. That means that we have 2 agreeing statements. That means that we have an agreement with the null hypothesis. That means we fail to reject the null hypothesis. So, what did we fail to reject? We failed to reject the idea that those 2 groups, the baby that took this enriched vitamin and the babies that took the regular vitamin, are the same. We failed to reject that idea. So what that means is that the baby that took the enriched vitamin and the babies that took the regular vitamins behaved the same, meaning that there is no difference, meaning that the vitamin probably didn't have an impact on walking age, not a significant impact anyways. So what you can say about this is that we tested an enriched vitamin to determine if it had a significant impact on walking ages. It was determined that the baby that took the enriched vitamin did not have a significantly different walking age than the babies that took the regular vitamin, and we conclude that the vitamin had no significant effect on walking. Wow, that's a long ways to go for such a simple finding, but once you get good at it, you get to do it a lot faster. And the good news is that I'm not going to ask you to do anything with this in terms of a data analysis. This is going to be something that we work toward getting good at before we do data analyses beginning in Chapter 7 again. So if you have questions on this, make sure you go back and review. Also use additional resources, ask questions, that's fine. You need to be able to understand the process of how to do this, at least at the basic level of understanding, so that you can kind of speak somewhat intellectually about the idea of rejecting or failing to reject the null hypothesis. Again, if you have questions, feel free to sing out. Do your discussion boards. Those can be very helpful. Also, do the chapter guides. And I will see you next time.